My name's Freeman. I'm a postdoctoral researcher at the University of Sheffield, and my work is split between direct energy deposition and laser powder bed fusion, but the work I'm here to talk to you about today is some of our recent laser powder bed fusion work, specifically looking at microstructurally graded lattices. So this feeds quite nicely on from our introductory talks this morning. We've got some metal materials, we've got microstructural control, and we've got damage tolerance. So coming on to what's the challenge, why have we done this? So with additive, we've seen lots of people talking about being able to create structural lattices. And they've got applications for all sorts of things, but particularly for energy absorption situations. So protective casings, for personal protective equipment, for blast impact protection. And what we're looking at is there an opportunity to tailor that response, to change the way that structural lattices behave, not just as a bulk material, but on a finer level. So picking up on what Matteo was talking about, but applying that concept within a structural lattice, so that we can direct the damage pathway away from the substrate. So as that impact wave moves through the material, it can actually be pushed off in different directions. And that really comes into, can we modify the mechanical response of that material? So how have we done this? Well, some time ago we developed a technique on 17.4 pH steel. So 17.4 is conventionally regarded as a martensitic steel. If you manufacture it or buy it in bulk conventionally, it will contain around 90 to 95% weight of martensite. And we found that when we build it on a laser powder bed fusion system, specifically here the Econity Mini that we've got at the University of Sheffield, we get the characteristic microstructure that you can see there on the right hand side. So we've got fairly large grains of the sort of 10 to up to 100 microns in size. And inside those grains, we see the classic solidification cells that we've heard discussed, again, particularly in Matteo's talk, talking about those solidification cells. And they're very fine, often around a micron in diameter, sometimes smaller, sometimes a bit bigger, all depending on the local cooling rates. But what we find is those high solidification rates actually suppress thermal martensite. So we're suppressing that martensite start temperature, and that's something that's been known about in the literature for a long time. So there's two references there. One was from Harry Badisha, talking about the effect of austenite grain size on the martensite start temperature. And when we suppress thermal martensite, what does that give us? Well, it gives us high levels of retained metastable austenite. And some of the work we've done, we've seen up to, or in excess of, just about 99% austenite as built. So this is something that you just can't get conventionally. You can't take 17.4 and process it conventionally and get an austenitic structure. But it also gives us something else, which is that the in-situ thermal strain that we commonly associate with additive manufacturing then triggers deformation martensite. So this is a really interesting phase transformation here. Because we can go thermally or we can go by deformation, we've got two routes for controlling how much martensite we end up with in our finished part. One other aspect of this to be aware of is that that deformation transformation can also be triggered by post-processing. So one of the things you may look at in this presentation and go, why hasn't she done EBSD? The reason is, if I polish the surface, I transform my product. So it's one of the challenges that we're actually looking at currently, is how do we characterize these materials when the sample processing itself changes what we're looking at. So, applying this then to structural lattices, we've got two equations up here on the graph. One is a volumetric energy density calculation, and one is a thermal strain calculation. So these are both available in the literature, and highlighted in red are the key parameters that I'm picking out for this work. So Q is our power, V is our scan velocity, and then we've also got these parameters T and W that appear in this thermal strain calculation. So this thermal strain calculation is a comparator. It's not calibrated to an actual value of strain, but it's a way of tuning or looking at, if I build with this set of parameters, how much strain am I putting in? It doesn't necessarily look at, is that on the component scale or the melt pool scale. It's a sort of global parameter. And in this instance, T is a characteristic time, and W is the length of the melt pool. So we can see there's a lot of overlap between energy density and thermal strain, but they're not identical. And we can play tunes with the scan velocity to affect how those balance out, and we can play tunes with the melt pool length and that characteristic time. So there's a lot of ways of tuning these two parameters against each other. We've started off with two different build parameters. There's a green one and a pink one. The green one is our low energy density parameter, so we can see a little lower on the power, a bit higher on the scan speed, and then the pink is our high energy density or high strain parameter, and we can see higher power and a much slower scan speed. What that gives us is a difference in energy density, but it also gives us a difference in strain. We've then taken those two parameter sets and applied them to structural lattices. So these have been basically just superimposed as composite structures on top of what's already a structural lattice geometry. So the lattice geometry we've used is a diamond cubic structure. So I mean, it's fairly common in the literature to start with diamond cubic and move on from there, so I'm sure you're aware of that as a structure. But what we're looking at here is applying that composite approach. So kind of the Lego bricks from earlier, but applied in a different way. So we started off with classifying it as a uniform structure, so the A1 and the A2 have just got those parameter sets applied uniformly. We've then looked at what if we split the geometry between the nodes and the struts, looked at horizontal layers and looked at vertical pillars. Picking up from a couple of the talks yesterday on lattices, there's also the opportunity to treat these as precipitates. So if we have one of those materials as a precipitate phase within a matrix of the other one. But what we're looking at is selectively suppressing and triggering that transformation by using strain, and that's the inbuilt strain. So the talk immediately before me, we were talking about residual strain as a problem, and I'm looking at it as a way to change what's happening, a parameter that I can use to tune what's going on. One aspect of this, the phase quantification we've had to do, is using squid. So squid is a magnetic technique, and squid has been useful for us here because we've been able to use it without having to do lots of surface preparation, and surface preparation would add additional transformation. So there's quite a lot going on here. But in terms of the outcome, so our high strain parameter, we've got around 43–44% of martensite. So that's our strong brittle phase, and therefore we've got around 55% austenite, which is our weak ductile phase. With our low strain parameters, we only get 3% martensite. So already we've seen perfect, good, we've achieved what we wanted in terms of our phases. Does it make a difference to what's happening? Slide. So we've tested these structures with quasi-static compression testing, which is a fairly classic place to start when looking at energy absorption structures. And I've got two videos, which I am sure should work. Yes, here we go. So on the left-hand side, we have the structure that was uniformly high strain parameters. So this is one with 40% of martensite. And we can see a classic stretch-dominated behavior where we get collapse of a layer, nothing, collapse of a layer, nothing. And it goes through in staggered stages. And that's the pink line that you can see on the graph there. So you can see takes the load, collapses, takes the load, collapses. The low strain parameters then, with very little martensite in them, we see a nice a bend-dominated structure, which is the one people are normally looking for. But this is where the whole structure takes up the load and then it just squashes gently as a complete thing. But what about all these composite ones we made? So, with the composite ones, we see intermediate behaviour. So we've got, with the nicest one I think probably is the horizontal layers, the C graphs, where we see some plateau behaviour and then we see some collapsing behaviour as well. So what this is telling us is that through this control of build parameters, with an intentional way of factoring in how much strain we're putting into different regions of the lattice, we're then able to control what phases we produce, and by controlling what phases we produce in a spatially distributed way, we can go on to produce composite structures where we've designed in specific microstructures in specific locations, and with that modify the mechanical response. So the set of coloured images in the bottom corner there are differential image contrast. They're all taken at around the same level of deformation, and we can see displacement patterns on there. So we're looking at moving where the displacement is taken up, how it moves through the material, which bit of the material is failing first. And that gives us confidence that we can then take this technique and go on with it to look at producing more damage-tolerant structures which have a higher level of control, which have a more tailored level of control, and with this, potentially also expanding that out to look at other material systems that exhibit phase transformations. Because if we can do this with one material, it should be possible to open it up and do it with other materials as well. So, are there any questions?